New Year greetings for 2022. Actually, this is the first activity of this Civil Engineering Sectional Committee organized for this year, according to our calendar. Yeah. And now we are about to commence this fourth lecture of medium-rise buildings, designs and constructions series. Today it will be explaining under the title Design Philosophy for Medium-rise Buildings of 15 to 20 ranges. Professor Jayasinghe, on behalf of the participants, I appreciate the steps taken to share your knowledge in this design area and actually shorten the responsibilities of Civil Engineering Sectional Committee. So I used to say that because it's very important. Dear participants, hope you will extract the deliverables from Professor on this valuable lecture series throughout the series actually. So I want to remind you two things now. One is actually I suggest you to raise your questions when the opportunity is given after each section. Professor will ask you to, is there any questions? So you can respond to that. It will be directly, you can negotiate your questions and it will be more effective. And I want to remind you to register for each session through MIS, like I have been reminding you la previous one also. Without further ado, I'll request you to enjoy the lecture this evening. And Professor, over to you. Thank you.
Thank you, Engineer Kamala. First, a very good and happy New Year, happy and prosperous New Year for all of you. And I also hope that you will have a lot of health and wealth in this year. So first, first day I talked to you about the general buildings. Then second day I told about the philosophy for very small buildings like 4 to 5. Then next day I went up to 10 stories. But when you move to 15 and more, the design philosophy changes. So we have to understand it. So when you do a computer model, 3D model, it will give you some answer. But the most important thing is finding whether the answer is right or wrong. That's very important. When you get an answer from the computer can be say garbage in, garbage out. So to do a wrong model, get wrong values, input wrong values, you'll end up with wrong answers. So whatever you get with computer, you should have simple ways of checking. And that's where the design philosophy comes. So when you know the design philosophy, when you get an answer from 3D model, you can straight away say whether it's a reasonable range or not a realistic answer. So that's why we always say, learn the design philosophy. At the university, you learn the codes. And again, now British codes are obsolete and we have to go for Euro codes. And Euro codes are very advanced. If you want to do very economical designs, you can do very economical designs with Euro codes because Euro code will allow you to go up to 105 megapascal concrete. And it will allow you to use steel with higher strength as well. You can go up to 550 steel if you are using Euro code or 600 steel. So all those possibilities are there with Euro codes. So it's up to you. First, learn the Euro codes. To learn the Euro codes, there are many textbooks, like textbooks by Musli and Banji, McGinley, and so on. So I request you to go through all those books because it's really difficult for me to teach how to use the code in a lecture series like this. What I can teach is, how to think about the design. How that is at a different level. So we are looking at the design philosophy and how it works and what are the important parameters that you look for. And what are the differences between one arrangement and another arrangement and so on. So, and also you should learn how to optimize. So before we optimize, first we have to get an answer. So first we look at design philosophy. And I'll be using same example, same number of floors, sorry, same arrangement, but first number of floors can be very different. So today we are trying to see how we can make use of, how we can use all the strong elements and the frames all together to make an efficient structure. Now, last time I told you, frame will carry only the vertical loads, walls will carry all the lateral loads. Now, today it's going to be different. Then you have to ask why it's going to be different. The reason is, when you have a very tall building, we have a cantilever. The shear wall is a cantilever. And a cantilever can have a large deflection if it is very long. So in the case of a 10-story building, the height is 36 meters. In the case of a 20-story building, the height is 72 meters. So there's a big difference between the heights. 72 meter
Excuse me,
wall.
Professor. Professor,
Yeah.
can you? Yeah. Have you opened the? I mean, still video is not on yet, no, for the participants.
No. I'm just
Okay, I
giving some
understand.
background. I'm just
Okay,
giving
yeah,
that
thanks.
comment, all right?
Okay.
So just the basic information before I start teaching on the board, right? Okay. Because they are still setting it up. No internet. There is a small internet problem for the computer. That's why I'm just, they are setting it up yet. So I'll first give the background. Right? So basically, if you would consider wall, shear wall, 6 meters of length, because in the design example, you will find the shear wall is 6 meters of length. So the shear wall is 6 meters of length. In a 10-story building, it's very strong because its height is only 36 meters. 36 divided by 10, 6 is 6. The length to the span of the beam to length ratio is 6. Whereas you go for 20-story building, then the height of the wall is 72 meters with floor to floor height of 3.6 meters, 72 meters. Still the wall length is 6 meters. So what will happen? What happens is the wall will be much more flexible, much more flexible. Then let's look at the frame. In the frame we use, what is the size of the column if it is a 20-story building? The size of the column can be something like 800 by 800. How about size of the beam? Beam doesn't change. Beam is still 600 by 400. So we don't have a problem with the beam. And how about the earthquake? Earthquake, no problem. Now the column is 800 by 800. Beam is 600 by 400. Any hinge forming will be in the beam. So no problem for us. So beams, the columns are large, beams are smaller. So we can use this column size for about 10 floors. What are we going to do about 10 floors? We can either use 600 by 600 because beam size is 600 by 400 or 600 by 350, still the beam is smaller. So we can use 600 by 600 depending on the loads. For example, if you have a building where the loads are higher, then what we do is, if the loads are high, what we do is you have to use a slightly larger beam. What is the reason? If the loads are high, flexural moments can be high, but most importantly, we have to think about shear. If the loads are high, shear also will be high. If the shear is high, what is better? A slightly bigger cross-section is better. Slightly bigger cross-section is better. And when the loads are high, bending moments are high, again the slightly higher width is better. Why? Because slightly higher width will allow us to have the reinforcement fixed easily. And when you have the loads high, shear is high, so we use 600 by 400, you will find the shear shear stresses will be lower. Shear stress will be lower, which will be a good thing because we don't want beams failing in shear. We always like beams failing in flexion. What is the reason? When a beam fails in flexion, we get a bigger warning than a beam failing in shear. So that is the reason. So you have to look at all these aspects separately and register it in your mind so that whenever you see a problem, straight away know the answer. In your mind, you can work it out. So if you have a building with heavy partitions, then the loads are high. Then bending moments will be high, shear forces will be high. Is it a good solution in these days? You know, these days, steel is very scarce in the world market, not in the Sri Lankan market. Because of that, in Sri Lanka also, steel prices have gone up to about 220,000 to 230,000 range, which means 1 ton of steel, how much money you have to spend? 350,000 rupees. 350,000 rupees. How about concrete? Again, a problem. What is the problem? Problem is concrete is now becoming gradually more expensive. Although it's not as expensive as steel because concrete anyway used to be expensive. So now the concrete prices are going up. One cubic meter of concrete is about now 23,000 rupees by the time you place it. Now you can see it's not good to use high amount of concrete in a building. It's not good to use high amount of steel in a building. So how to reduce the amount of steel in a building? In the slab, we'll have secondary beams and we'll reduce the spans. Then we can easily go for a slab of 125 to 140 or even 150. And again, you'll ask, why 140? Why don't you go for 150? Then I have to ask the question, why do you want to change in 25 millimeter intervals? Why can't you change in 10 millimeter intervals? At construction site, we can change in 10 millimeter intervals. Why? If you save 10 millimeters every floor, if you're having 20 floors, we are going to save 20 centimeters. 20 centimeters means, you know, it's about 1.5 slabs. So you are saving the weight of 1.5 slabs. So that's the way you have to look at it. So it's good to go for secondary beams, reduce the thickness of the slab. And when you reduce the thickness of the slab, because it's all supported with an efficient system, then you'll find the reinforcement needed is much smaller. Reinforcement needed is much smaller. And you'll find the reinforcement requirement is only 10 millimeter bars at 250. Whereas if you go without secondary beams, the reinforcement requirement can go up to about 10 millimeter bars at 125 or 150 millimeters. So you can see, in your mind, you have to clearly see it's good to go with secondary beams. Similarly, you have to think about the beams. When you have less thickness for the slab, what can you say about the dead weight of the building? Dead weight is less, so the bending moment due to dead weight will be less. And if it is less, you can reduce the reinforcement in the beam. You can reduce the reinforcement in the beam. You can't do anything about live loads, but you can do a lot about partitions. These days, you know, no need to go for solid block partitions. If you want to go for a partition wall, you are using hollow block work is about 12 to 13 kilonewtons per meter cubed. Whereas in the case of solid block work, the density is about 20 to 21 kilonewtons per meter cubed. So if you can use hollow block work, why do you recommend solid block? That's the one question. Similarly, there are so many lightweight options. We have autoclave blocks manufactured in Sri Lanka using waste materials. If you look at cement sand blocks, we are using either crushed aggregates or river sand or quarry dust or something to make it. But if you start using a lightweight block for partitions, what can you say about the impact on the reinforcement in the slab? You can reduce the reinforcement in the slab. Why? The partition load is very small. The extra moment due to partition is very small. So you might need only a small extra reinforcement in that area as a band so that the partition load can be taken. Something simple. On the other hand, you insist that we need brick walls, 9-inch brick walls, one big thick brick walls. Then we are adding huge loads onto the slabs and onto the beams. What are the repercussions? Higher the load, higher the dead weight. We need more reinforcement, larger beams, or both to carry high loads. So what should be the future trend? Future trend is we have to minimize the carbon footprint of a building. And carbon consists of two options. One is the carbon embedded in the material. That means the carbon that we need to emit to manufacture 1 meter cube of concrete. That includes the energy needed for crushing the aggregates. That includes the energy needed for making 1 kilogram of cement. It includes the energy needed to run machinery, and it also includes the energy needed for transportation. So if you want to reduce the carbon footprint of a building, what is the best option? Option number 1, minimize the amount of material that is used. So instead of using, saying that it's easier to do the formwork and doing a flat slab or large slab of 6 meter by 6 meter, you can save a lot by doing a slab of 125 or 135 or 140 millimeters with a second beam system. You can save a lot. Then you'll ask, on what basis? You quantify all this. So what we do is, we look at the total quantity of concrete, we look at the total quantity of steel in the building, and then when you look at the total area of the building, we can say how much energy is needed to construct 1 meter squared of the building. And that way we can do a comparative study. One is a slab without secondary beam, another is slab with secondary beams. So we have two options. One option is where you have a slab with secondary beams. The other one is where you have one without secondary beams. And then you will also look at the beams. Then only thing is, if you look at the volume of concrete in the beams, whether you use 350 or 400, you are not going to gain a lot. So if you think 400 is going to make the construction easier, go for it. But don't say construction is easier for slabs, because our labor rates are still not very high. Our material rates are higher. So saying that saving concrete is always better than making the construction easy in Sri Lanka. So we have to always look at this and see what is the best strategy, because strategies can vary depending on the price of labor, depending on the price of materials. Now in some countries, saving labor is very important because labor is about 3 to 4 times more expensive than materials. In Sri Lanka, it's the other way around. So none of the theories they develop for other countries is applicable to Sri Lanka, because still our materials are more expensive than labor. So when you do partial automation, we can reduce the labor, but we need still have labor, but in many countries, anything that you say with labor is extremely important. So they go for flat slabs and they say flat slabs are the best. May not be in Sri Lanka. Can you hear me now?
Yeah.
Yes.
Yes.
There was a call and there's a. So based on all this discussion, what you can see is always we have to think about the construction cost, not as a fixed value, as a variable value. And from time to time, we may have to change the strategies. And in the present context, best strategy is minimize the amount of materials used. And second strategy is minimize the amount of operations that you need before we complete the bill. So the two strategies, one is minimize the amount of material needed. Secondly, minimize the amount of operations needed. For example, if we can use a block that we don't need plaster, then we are in a normal traditional way. We have the block work. We don't construct the wall properly, so we are plaster both sides. So that needs sand, a resource, scarce resource. On the other hand, if you go with a very neatly done block, like lightweight autoclave block, the block can be slightly more expensive, but what you find is you don't need plastering. And because you don't need plastering, you can save labor and you can save time. And time is money. Because if you can deliver a building with a lower duration, then you can make a bigger profit. And the clients also will be happier because then it will add to your reputation of your company. So always think about these aspects. And it's very important we start thinking about going for new materials, lightweight materials, and also waste-based materials. Why? The moment you use waste, the carbon footprint of waste materials is zero. Carbon footprint is zero, which means you can end up with low carbon buildings. You can end up with low carbon buildings. So with that introduction, so today we'll start looking at the buildings going up to 20 floors. So I draw the same building. This is 7.5 meters. And this way 6 meters. So there's a building. And we got the grid. Here you get the grid A, B, C, D, E. So there is the grid. Then we have the shear wall.
Okay, so share the screen now.
Yeah, just one moment. You get the screen. Okay. Can you see the board now?
Not yet.
Yeah, just one minute.
Yes, computer screen. Okay.
Okay. Can you make it bigger? Huh? Yeah. So
So we can see now.
you can see it now?
Yes.
Some says
Okay.
but we
Yes, yes, we can see now.
Yes, see now.
Cannot see.
Can't see. Can't see.
not all.
You
I mean,
Now we can.
who is the host? Can you, because I am getting,
Sir, we have to select the screen.
yeah, that's the thing. The screen is small. That's the problem. Huh? Can the host change the size of the screen?
No, I think the person who don't see the screen just double click on the screen with the whiteboard.
Yeah, that's right. That's right. That is true. Exit. Escape to double click and exit to. The big screen is not appearing on my computer. That is the problem. What is this one? Huh? Going on. Maybe host screen. Host. This is not my screen. That's right. I mean, still can't. You can't see it. See the screen.
I
We are
think
seeing Ratna's
some
screen.
of the crowd can see, but still even I cannot see.
Yeah. So can you make me the host for a moment? I think then I can. I should be able to sort
Yeah,
this out.
ISL has to do. Manjula.
Oh, man. Yeah, now what is shared is not my screen. I can't show my screen. That's the problem.
I think Ratna is sharing his screen. He has
Yeah,
to
that's the
stop
thing. That's the thing. Somebody, the host has to. Host is sharing his screen.
Oh, it's okay, sir.
Is it? Paul? Can all see the large screen?
Okay, sir.
No, we can't see.
We
No,
can't
some
see.
can't see. Some still can't see.
We can't see.
Yeah, now okay.
We cannot see. Those who cannot see, just double click on the screen with the whiteboard.
Whose one?
Nothing is there.
I can't make it full screen.
Yeah, sir. Now your
Oh, yeah,
screen
yeah,
is
okay.
shared already.
Accept. Okay. මගේ ස්ක්‍රීන් එක වෙනස් කරන්න අර මේව නැතුව මේක විතර ඩබල් ක්ලික් Yeah. Oh, yeah, host has to do that.
First pin कराना.
Host is ISL, is that right? Yeah, host is Civil Engineering Sectional Committee. Is the host. Yeah, we can't do anything. Host has to do it. I think host can see my white screen and they have to make it bigger.
So those who don't see the screen, just find there's a two login from the say M.T.R. Jayasinghe. There's two login. One is from your phone. The other one is your computer. So they have to select the computer and double click on it.
See, it's not working on my computer. That phone, I have turned off the camera. When I double click on, even on my screen, when I double click, still doesn't appear.
So we can see the screen.
Some can see the screen, that's the whole problem.
Sir, could
Now
you?
I can. Even
Sir,
I can see. I think everyone can see.
We are not seeing.
Yeah, those who
Can
are
everybody see the screen? Then I can continue. I don't have to see my
those who are
screen.
on the phone, you can drag the screen onto your left, so you can see the participants, and the sir's window is also there. So just double click that. Those who are using the phones.
Yeah, it's working. If you are using the phone, double click on the small one, then it will
Yes,
work.
sir. Yes, that's what we have to do.
That advice work. Now it's working, is that right? Shall I continue?
Yeah, it's working.
Yes.
It's working, yeah. Shall I? Okay, I'm continuing.
We can't see.
We can't see.
Oh, you can't see?
Yeah.
I can see on my phone. If you can't see on the computer, can you log on with the phone?
Yeah, that's better. That's better.
Yeah, that's better. Yes. If they have a problem with, I'm also having a problem with my computer, but I don't have a problem with my phone.
So can I give suggestion?
I can't.
Please, others don't share your screens.
Mr. Manjula, can you be the host and how many are there who can't see the screen?
We can't see. I don't know.
I can't see, sir.
We can't see this.
Yeah, I think just to fix this problem. I can't do anything at this end because I'm not the host.
I can see in the phone.
In the computer, you can try the pinning option. In the gallery, if you go to the gallery, 3 dots.
Yeah.
Then you have to, there's an option for pinning.
Pin. Yeah, it works. It works now.
Yes, sir. Yeah.
It came and went back.
Others don't share the screen. Sam Ratnawali is sharing the screen now. Please.
Yeah, somebody else is sharing the screen.
can the host stop this from sharing the screen? The host can do that.
Now this is on my screen. What you see is on my screen.
Yeah,
MBC Ratnamali, can you switch off the screen?
okay.
Okay, now we can see.
We can't see.
Huh?
We
Again,
can't see.
go to the
Do the
pin option.
pinning.
Pin option, yeah.
Try
Go
pin
to
option.
gallery.
It might work.
Yeah, go to the gallery, then pins as whiteboard.
Gallery is 3 dots. Gallery is 3 dots. Is that right?
Yeah, that's right.
3 dots and then
And pin, yeah.
now I can see it full screen. How about others?
Now we can see.
I think it's okay. Like we can
Now we can
Yeah,
see.
okay. Then shall I move forward?
Yes, sir, yeah.
Okay.
I think you
Right.
can proceed if someone is there.
Yeah.
Fine.
Yeah. So basically we are 6 meters here. 6 meters here. And last time I showed you that we have to balance and make it as much as possible non-twisting. So we have to make it as non-twisting as possible. As non-twisting as possible. And this side you get 7.5 meters. And let's say these are 2.5 meters. And so on. So, the first thing is, what is the behavior? We have 20-story building. I'm talking about the wind acting in y direction. So if you take the wall is a cantilever. So what is the way that it deflects? Theta 0 here, delta 0. Delta, you will have some value. That is the way it's going to behave. But if you have a column, how will it bend? Like this or like this? If you have a column, how would it behave? A or B? Columns always behave like this. Double curvature bending. Double curvature bending, not single curvature bending. Columns will always behave like double curvature bending. Double curvature bending. So which means when you have a frame, it's going to behave like this. Theta max here, delta 0. Here theta 0, delta, you have some value. So this is called shear mode. Here it's called cantilever mode. This is called cantilever. It's a cantilever. Shear wall is a cantilever. Whereas the frame will behave in a racking mode or shear mode. And all the columns will go into double curvature bending. So because of that, you get a maximum curvature at the bottom, 0 curvature at the top, 0 deflection at the bottom, some deflection at the top. Now, can you have two different behaviors in one building? We can't. So what we do is, we combine them. And when you combine, what is the dominant behavior at the bottom? Dominant behavior is wall. So wall dominates. And what is the dominant behavior at the top? Wall is very flexible because it's very tall. So it goes like this and comes back. Goes like that and comes back. So generally we expect it to be cantilever, but that is not the way buildings behave. The building will have the zero curvature at the bottom because it's dominant. Frame is very weak when you compare the strength of the wall. But at the top of the wall is so flexible, frame is stronger. So what happens is, we get a very strange deflection pattern where the building is coming back at the top. So this is called wall frame interaction. Wall frame interaction. The wall is interacting with the frame. Wall is interacting with the frame. We call it wall frame interaction. We call it wall frame interaction. So when you have wall frame interaction, how do you deal with it? How do you deal with it? So for that, I will say the column sizes are 800 by 800. We say the beam sizes are something like 600 by 400. Because we are going to have 20 stories of wall, we'll select 250 millimeters for the thickness. We don't want to cramp it too much so that it's very difficult to do the construction. So it's very much easier when the wall thickness is 250 to do the construction. 225 generally comfortable. 200 you struggle a little bit. 225 generally okay. 250 very comfortable. Very comfortable. So when it comes to concreting, very comfortable thickness is 250. It doesn't mean you can't do 200. If you want to do 200, do it. No problem. But you have to struggle a little bit. And you have to make sure sometimes you get a higher slump for concreting and so on. So, right, now, how do you deal with this? When things are interacting like this, can you do manual calculations? No, we can't do manual calculations. Can you do a 3D model? Yes. But if you are doing a 3D model, you should know what's going on. So to understand what's going on, it's very much easier to do a 2D model and understand what's going on. So what you do is, when you are doing a 2D model, I'm going to lump this frame with this frame. Frame A and E, I'm going to lump. Why? I have full frame there. How about these two frames? They are not full. So I'm going to ignore those two frames, but I'm going to consider all these shear walls. So I can make a model. Model is shear walls. Then I will have a wall, the frame. Frame. Now the sizes. How many walls I'm lumping here? 3 walls. So I'm going to say I have 1 wall, another wall, another wall. 3 walls. What is the thickness of 3 walls? 750. What is the length of the walls? 6,000. So what happens here? I'm going to have 2 columns lumped like this. You have to be careful in the direction when you do the graphics in the computer program and see which direction you have given the properties. Why? We have this column and this column lumped together. You have these 2 columns lumped together. I said I am going to ignore all the other small frames because they are not real frames. Now, what happens at each floor level? At each floor level, we have a slab and we call it a rigid diaphragm. A rigid diaphragm. If you have a rigid diaphragm, what we can say is the deflection at these two should be the same. So what we do is use some links which are pin-ended at the ends. We combine them. And then we apply the loads. Either at the floor level or as a UDL or something, we apply the loads. So because we need a joint, we consider it this way. So in the model, we make the wall. Basically, we use a column, but we give the second mortar area in the correct direction. And about which axis you calculate the second mortar area? This axis of bending. You have to calculate the second mortar area about that axis. You have to calculate second mortar area about that axis. Why? It bends like this, so the axis of bending is that. So the I value of this is 1/12 B D cubed, that is 1/12. Breadth is 750, length is 6,000 cubed. That is the value. That is the value. So you have to carefully select the axis of bending by using right-hand corkscrew rule, and then you have to get the second mortar area right. So what happens is, if you look at the external, the bending moment due to external loads, it will go like this, sorry. It will go like this. This is the bending moment due to external loads. Then if you look at the bending moment carried by the wall, it will do something like this. And the bending moments carried by the wall, it will do something like this. So finally, you will find at the top of the top frame is carrying more bending moment than the wall. Basically, frame is restraining the movement of the wall. Or we are saying frame is stronger at the top. Because of this behavior, let's take the topmost floor. Can you use a 300 by 300 column? Axial loads are very small. Can you use a 300 by 300 column? It's the top floor of the building. Can you use a 300 by 300 column? It's wrong. Why? Because of this wall frame interaction, if you use a very small column, it can be damaged. So that's why we generally don't use any column size less than 600 by 600 in a building, because if you use a smaller column size, this interaction can make it to fail. Might make it to fail. So the minimal size of the column at the top of a tall building will be 600 by 600 daily in the column. Why? So you have to make sure frame is strong frame. You do not reduce the size of the column very much. You maintain the size. Is that clear? Any question you want to ask from this? So are there any questions on the chat channel that we can answer? Are there any questions on the chat?
Yeah. So when we model 2D model, make the 2D model, the two columns come into one. So we make
Yes.
it as 1.6 by 800. Is it-
Yeah, 1.6 by 800, but when you consider the I value of this is 1/8 into 1,600 into 800 cubes. 800 cubed.
Okay.
Is
Yeah.
that clear? 1,600 into 800 cubed. Because axis of bending is here. Axis of bending is that. Is that clear? Axis of bending is same as the wall. So you are just increasing the width. You are not improving the second amount of area. You are just doubling the second amount of area, because what you increase is the width when you lump together, not the length. Is that clear?
Yes, sir. Thank you.
Okay. So
This
once
is
you do this,
one
you can
question is
easily
there.
make a model. Sorry.
Yeah. There is one question.
Yeah.
Please explain the diaphragm action.
I explain, right. Okay, now just take a half sheet. Can you bend the half sheet out of its plane? Very easy. Can you bend the half sheet on its plane? You take your phone. Can you bend it on its own plane? Very difficult. But if you want to bend the phone, you might be able to do it out of plane. So any plate is very strong in its own plane. So walls, and if you look at this diagram, we have slabs here. All these slabs are connecting frames and walls. And that is called diaphragm action. That is called diaphragm action. Diaphragm will measure, if you take the deflection of any point, because we know the relative location of points, if you know the deflection of one point, you know the rotation of another same point, then you can predict the deflection of other points and the rotation. Which means walls and frames are not free to move as they wish. Walls and frames are not free to move as they wish. The movements are restrained, and that is called diaphragm action. Diaphragm comes with the slab. But if you have precast slabs, not very strong, not properly connected, then this assumption may be wrong. So you have to be very careful with the type of flow system you select. But as far as you do any in-situ cast construction, diaphragm action is there. But if you are using a lot of free cast, you have to be careful. You have to have sufficient screed at the top with some reinforcement so that all the precast members will not have any relative movement with respect to the next one. The moment you do that, you can say it's a strong diaphragm. Is that clear? Is that clear? Any other question?
Yeah, at the beginning there was a question. Can we detail a beam to meet seismic mitigation? Within bracket, not to follow the simplified Curtanian rules while calculating the amount of reinforcement as per BS 8110.
No. That is not the correct way. What you have to see is, if you have a column, sorry, if you have a cube, concrete cube, apply the loads, what will happen? It will break at some load. At some load, it will break. But if you put a lot of reinforcement in the cube, and the reinforcement is now preventing the expansion of the cube. So what happens when you apply the load this way? There will be a stress this way. So when you apply the load that way, there will be a stress in the lateral direction. Now by putting some reinforcement, we restrain the lateral movement, lateral stress. Then what will happen? We say, now the cube is in a triaxial stress state. Triaxial stress state. So what we do is, we provide some links at reasonable spacing, like T8 at 75 millimeters over 600 millimeters of the beam. And then we say we create a triaxial stress state in the beam. So when the beam crushes, concrete will not crush, concrete will remain its ductility. So concrete will crack, but it will not break into pieces. So to prevent the concrete breaking into pieces, what we do? We simply ensure there's a lot of links around the concrete. So the concrete will go into a triaxial stress state, and in the triaxial stress state, concrete is much stronger, so it will not crack. Is that clear? Because basically BS 8110 does not cover any earthquake detail. Any questions?
One more is, what are the properties of the struts connecting the wall and frame?
All right, okay, very good question. This is just a beam because we are representing the deflection at these two places are the same. So it can be something like 400 by 400 beam, something like that would do. Anything that can that will not deform too much axially, it's okay. How about frictional strength? No need. Why? We have two pins at the ends. So you have to make sure it has a sufficiently large cross section so that whatever the load I apply here can be transferred onto the frame. That is the requirement. So you can select an arbitrary beam size because you are representing a slab. Any other question?
The last one, please
Yeah.
explain axial shortening in the column and how to provide reinforcement for that.
Don't worry about it because axial shortening is not critical in the 20-story range. Axial shortening of columns will become critical only in the range of 30, 40 and so on. There are so many different ways to deal with it. One way is, you will use reinforcement to deal with it. You provide more reinforcement in the column and little more extra reinforcement in the wall. Then you can start changing the axial shortening. More reinforcement is difficult for the concrete to push up. The other option is when you want grade 30 concrete, you use grade 50 concrete. So grade 50 concrete, the elastic value is high, then the axial shortening will be less. So there are so many different options to deal with axial shortening, but not in this range. This range, we really don't worry about axial shortening. So axial shortening will be really small because our loads will not be high enough to cause significant axial shortening. Is that all?
Yeah, Professor.
Right, then I can move
Yes.
further. So basically when you do this, you can get an idea. Now they have a question. When it comes to design, how to design the wall? Wall can be designed as I explained last time. You know the moment in the wall. You know the moment in all three walls here. Because computer program will give the moment on the wall. It will give a bending moment diagram for the wall. So concrete wall is strong. You get a high moment in the wall, but it is to get the moment on one wall, you have to divide this answer m by 3. If the total moment is m, the actual design moment is m by 3. Because you have lumped 3 walls together, so the moment on one wall is m divided by 3. Similarly for the columns, we are lumping 2 frames, whatever the moment in the column divided by 2. Then how about axial load? Axial load we can calculate. For each wall we know the axial load. We can calculate the axial load by considering how much load is transferred onto the wall. So if you take this wall, this amount of load will be transferred onto this wall. You know that. So you can always estimate it. So basically, you have a wall where we know N, where we know M. If you know both N and M, can you design the wall? Yes. I explained you how to design the 6 meter long wall last time. Same method. But because the structure is taller, what can you say about the bending moment? Bending moment values can be higher. So you have to make sure axial loads are sufficiently large. Then I said, all these columns in this part of the structure, columns are stronger than the wall. So who governs the reflection? Frame. Then the question is, do you have to design these columns as braced or unbraced? We design them as braced. Why? Although it reduces the deflection, if something goes wrong, column can still hold it. Column can still hold it. So because of that reason, these columns can be designed as short columns if they have a large cross section and flow to flow height is reasonable. You'll always find columns are short. Columns are short. We like short columns. I like short columns. Why? Short columns never fail in buckling. Short columns never fail in buckling. And I hate buckling. Why? I have no control. I have no control of buckling. So I hate buckling. So what I do is I do not select anything that can lead to buckling, which means I will ensure that the column cross section is large enough so that it can be considered as a short column. So column is okay. You can calculate the loads on the wall. You can get the bending moment on the wall from the program. Now we know the bending moment and axial force, we can design it. And same way we can get the wind moments on the wind-induced moments on the frame. And based on that, we can say each frame will be carrying this much of bending moment. And so there will be a bending moment diagram like this with point of control flexure, something like that. A bending moment diagram where the maximum bending moment occurs just below the beam and the zero moment occurs at the center. So the bending moment here is zero. So we get a diagram like that. By using that diagram, we can do the column design because we know the axial force, bending, and the additional bending moment due to wind loads, lateral loads. In addition to that, we know the bending moment due to vertical loads. So which means you can find the critical values and then select reinforcement for the critical sections. And then if you think it is reasonably low, then you can actually design all the other, detail all the other beams in a similar way. Right? So you'll get only this kind of diagram as the bending moment diagram from this analysis because we are not considering any dead and imposed loads. And most importantly, what we get is how to design the cantilever wall with interaction. So whatever is due to interaction, you get a reduced bending moment at the base. So now you can see the design philosophy clearly. Design philosophy is, it is wrong to assume that all the lateral loads will now be taken by the wall because wall is going to be little too flexible at the top. Because of that reason, we should select the wall frame interaction mode. And we should not optimize the frame too much at the top, because we can get high bending moments and high shear forces. So don't try to make it very small, like in a two-story house. There's no difference between the flow. If you are dealing only with the vertical loads, there isn't much difference between. Sorry, if you are if you have any structure with less than 10 floors, it's correct to assume that all the lateral loads are taken by wall. But if you have 20 floors, it is wrong to assume that all the lateral loads are taken by walls. Only part of the lateral loads will be taken by the wall. Frame also will carry some load. Because of that, we have to consider the interaction between wall and the frame. So simple. So you'll work out some rules like that. For each story range, you have your own set of rules. The moment you look at a building, you ask how many stories. If it is 18 floors, now you know you are in the range where you have to consider the interaction between wall and the frame. Then what you do is you can do some preliminary calculations like this. And if you are at the preliminary stage, you can get some idea about the bending moments. And once you have some idea, then you can go for the proper three-dimensional model. And when you prepare a 3D model, you will have a lot of complications. And if you don't do this kind of simple calculation, when the complications come, there's a general tendency to think that the model is correct. But the problem is, if you don't have a simple model, there's no way you can check the results of the 3D model. So always go for a simple model, get some idea. Then with that idea, you can go for a 3D model. What is the difference? If you just do a 3D model, you have no idea about the answers. If you do some simple calculation like this, look at your rules, you know what is happening. Now you do your 3D model and you get some answers. You know whether they are the right answers or the wrong answers. Why? From the simple model, you know what's going on. Is that clear? Is that clear?
Yes, sir.
That's clear, right? So basically, this is the design philosophy. And I assume that you are capable of doing 3D model, but don't worry if you are not capable. Don't worry. I'll be teaching that. One of these days, I'll teach you how to design, how to model, how to make a 3D model of a building using SAP 2000. Then you'll ask why you use SAP 2000. The reason for using SAP 2000 is, as a teaching tool, I can teach you all the simple things using SAP 2000. But as a design office practice, we know ETABS is a dedicated program for buildings, whereas SAP 2000 is a general program. Which one should suit better? You'll find ETABS is better. Then at Marathon University, we have now deviated from SAP and ETABS. We still use it for most of our activities, but we are promoting another program, that's MIDAS. The reason is we can get web-based license and you can have access to the whole MIDAS family of software. There's a huge advantage because it's by the same people, they always ensure compatibility. So when you make a model of a superstructure by using MIDAS Gen, you can transfer data easily for MIDAS GTX for advanced foundation model. And all the students at Boroto University are having a web-based license, and we hope that other universities also will consider this seriously and get that kind of facilities for the students. And the cost is only 2 point. Actually, every year we have to pay 7,500 rupees as the maintenance fee. And in our case, we bought it for about something like 30,000 rupee. One, we were given 25,000. We were given it at 25,000, and then they said we requested we are going to make the payment in 2 stages. So we made the payment by using money available over 2 years. So any questions on this? So I'm going to wind up the lecture because the design philosophy part is over. It's a matter of the participants looking at 3D modeling. And one important thing I told you, this model can give the bending moment on the frame, members, beams. It can give it for columns. And then all the columns can be designed as if they are braced. A big relief. Because I hate buckling. Because buckling I can't control, so I hate it. I don't like it. I will one day or the other do something so that I will end up with a short column. But if I have to design for buckling, then the column has to be very lightweight. The very lightly loaded column, then it's possible. But if you have a very heavily loaded column, then you cannot strictly judge whether it will buckle or fail in crushing of concrete. So because of that, we don't like unrestrained columns. And all the columns are in a braced structure, so they can be designed as braced columns. And the wall can be designed and some reinforcement can be selected. And if the piling contractor is in a hurry, you can give details. Why? You know the bending moments. So that's the advantage. Or doing a simple 2D model, rather than worrying a lot about a large 3D model, what I say is do both. Do a quick one so that you have some answers for any question that will come to your mind. Properly. In a proper 3D model. So basically, those are things I just want to tell you. And by doing a simple model, always you can get a lot of information. And most importantly, you can understand the level of interaction. You can see whether this change, point of contraflexion, occurs at a very low level or a high level. If it is taking place at a low level, that means you are having very weak walls. And you might consider increasing the width of the wall or length of the wall or do something so that they will become stronger. And if it's happening at the very top, that means your walls are very strong, they are very long and so on. But if it is happening in the upper 1/3, then you might say, looks okay, it looks okay. The sizing looks okay. Why? The change in the wall becomes weaker only in the upper 1/3 of the building. Upper 1/3 of the building. Not in the middle of the building. So this way you got the proportions reasonably okay. Reasonably okay. Any questions?
There's one hand raise situation.
Yeah, what is it? Umapati. Umapati, what's your question?
Yes, regarding lapping of rebar for walls and column, which area is good to lap? Is in the middle of the floor, each floor, or other area. In
No,
the second question,
there's no, yeah, we have to understand we are living in a very low intensity earthquake region. The last significant earthquake occurred 400 years ago on 1614 April 14th. 1614 April 14th. Nearly 400 years ago. And that also had a magnitude of around 6. That is the estimate. So basically, we are living in a very safe, one of the safest locations in the world. So we should not worry about earthquakes. That is the reality. But with time, we must consider designing buildings which can last not 100 years, 300, 400 years. Why? Because now Eurocode allows us to use better materials, high-strength materials, new techniques. So we should think of designing buildings so that once constructed, you don't have to demolish it. You can always repair and use it, So to do that, we have to come up with more advanced materials as allowed in Eurocodes, high-strength materials and so on. And because it's going to last longer, the chance of it being hit by an earthquake is high. So because of that reason, we can take some precautions. So don't overdo it, because we are not in an area where the earthquakes are high, so which means you can simply lap anywhere in the wall. If you want, you can lap right on top of the floor slab, or else you can lap it in the middle. Doesn't matter. Do whatever you like. Both will be similar for the earthquake range that can hit Sri Lanka. The earthquake in Sri Lanka will be very low magnitude. And only thing is, if an earthquake of 6 can hit Colombo, it can cause some damage. So there are two options. One is have some reinforcement to control the earthquake. What is the other option available? If you have a good building and you have some precautions, still you can get an insurance policy also. So that if something goes wrong, something cracks appear, there will be enough money for repair. And that will be a useful exercise. Because, we should not rely only on the structure. We can rely on other mechanisms as well. One of the mechanisms that will allow to share the risk is insurance. So you can think of, insuring the building for all kinds of hazards. And the insurance company also will do it happily because they know for sure you are not going to apply for. Your claim need not be honored because there will not be a claim. Every year you will pay a small amount of money, but there will not be a claim because the earthquake will not hit Sri Lanka. An earthquake of significant magnitude cannot hit Sri Lanka. But again, you cannot give 100% guarantee. And that's why we recommend do something. But don't try to overdo it, thinking that, you are in Italy. We are not in Italy. Right? In Italy, yes, you have to be really careful. Why? Every 5-10 years, or even every 2 years, you will find an earthquake has hit somewhere in Italy. 2 to 3 years. In Japan, yes, very high earthquake range. But in Sri Lanka, the chances of an earthquake of significant magnitude hitting Colombo is remote. But because we cannot rule it out fully, we can take some precautions. Is that clear?
yes, thank you, sir.
Yeah. Nishan Galagi?
Yes, sir.
Yeah.
So when you divide that bending moment between walls and frame, and so do you expect us to do 2D
No,
frame.
don't do anything. Computer program will do everything. You don't do anything manually.
Okay.
Computer program will plot the bending moment diagram for frame and the cantilever. You don't do anything. You don't have to do anything. You have to create the model. Once you create the 2D model for the 3D structure, you can work out what's going on. But then you can go for a 3D model and do the design. Initially, do some hand calculations so that you know what's going to happen. Just to get some idea, especially in the initial stages of doing 20-story building range, do all these extra calculations. After a while, you will find there's no need to do any of these extra calculations. But if you are venturing into something like you have designed 8-story building, now you want to design a 15-story building under the supervision of another engineer, so that you can go for 20-story license. Then do all these extra things so that you will feel confident. And you will also feel that you have understood the behavior of the building. Have I answered most of the questions? It's almost 8:30. Shall we wind up?
Yes, sir. Yeah, there are several questions, but is there any other method of? Sure, we can. Actually,
No, you can ask. You can ask for. I'll give you come.
Sorry.
You can ask.
Okay. In the computer modeling, we model wall as a frame element rather than shell element in order to read bending moment values directly. Is it okay? Sir.
Yeah, you can model it as a column. But if you can model it as a column, why? When you get the bending moment, only thing is when you model it as a column, I value is big. I value is this value. So program knows, although you have modeled it as a column, it's a wall. Program knows it. Program knows it's a very strong element. Why? I value is very high. Program knows. So we don't have to worry too much about it. Program knows that it's modeling. But if you want to model the real wall without using the shell elements, what you do is model it like this. You go to rigid arms, represent the width of the wall. So here do it. In the middle, you will put some rigid arms, massless rigid arms. And rigid arms will ensure, now we are representing the width of the wall. So introducing rigid arms is the only option that you can have if you don't have shell elements. So because you are doing some temporary calculation, you don't worry about shell elements. You simply consider it as a column with rigid arms. Any other question?
What will be the most suitable design load combinations for a structure of this type?
It's very hard to say because you have to consider the 1.4 GK plus 1.4 WK, or if you are using Eurocode, they have given. I'm actually going to conduct a lecture on that because it's a little complicated than what you think. It's a little more complicated than the Eurocode, the British code. So ideal thing is I have a lecture on masonry, and I teach how you consider different combinations. And it is valid for concrete as well. So we will make use of that particular note and learn it. I have a PowerPoint presentation to that effect. So I'll use that PowerPoint presentation another day and teach how to create load combinations for Eurocode designs. So until that time, you can think something similar to the British code ones. That is okay, but it's hard to say which one is governing. So you consider all. You should consider all and see, draw an envelope and get it. You don't draw, but you just look at it and see what's going on. Any other question?
Yeah, how to model wall column combination in the basement walls?
That's a different thing, and I'll be teaching the raft foundations and cellular rafts and so on. I'll show you how to do that.
Next one is how to do imposed load reduction in floors.
Imposed load reduction in floors. Generally, imposed reduction is not a big problem because it comes like 10%. So 2 floors 10%, 3 floors 20%, 4 floors 30%, 5 to 10, 40%, 10 to anything, 50%. So you can see, here I went for 40-story building, 20-story building, the live load reduction will be in the range of 50%. If you are designing a building having 8 floors, the maximum live load reduction will be 40%. And if you're having only 3 floors, you can go up to only about 30%. Is that clear? So in the computer program, very easily you can do it. Very easily you can do it. Anything else?
Sir, hello.
Yeah.
Sir, for clarification, please. So now in this 2D model, we considered, we lumped the frame along grid A and E plus the wall in the B and C grids, along the B and C, B, C, D.
B, C, and D.
Yeah.
Here you get one.
So now,
here you get another. Here you get another. Three
so
walls.
should we? Yeah, thank you, sir. Should we consider the frames attaching to these walls also?
No, actually, when you look at the frame, the depth of the frame is important. Here, you don't have a depth of the frame. That's why I ignored it.
Right.
If you want, you can consider that also. No problem.
So, can we just disregard these 2 exterior frames and consider the separate frames B, C, D?
No, always
with the wall and
when you are modeling, consider the big frame. The big frame is a strong one. So don't leave out the big frames. Use all the big frames, and then lump the walls. But if you have small frames, you can ignore it. There will be small error, but we are not looking at the exact answer. This is just an initial calculation to understand what's going on with respect to the beam sizes, column sizes, and so on. After that, you'd better do a 3D model for a 20-story building or 80-story building. You do a 3D model, and in the 3D model, you can capture all the things. But this is just an approximate calculation, just to get some idea about it. Before you design the real building, you'll do few simple models and see what's going on. And that way, if you do it for about 1 or 2 days, then you will get to know about your building fully. And after that, you can easily do the design. So you know what's going on. So these are just tools to us to understand what's going on. For design, always go for a 3D, ETAPSO, MIDAS model. Is that clear?
Yes, sir. Very, very much clear. Thank you, sir.
Yeah.
Thank you very much.
Yeah. Okay. Shall we wind up because now?
Yes, sir. I think there are many questions, but I think it's running out of time, no?
Yeah. So basically, you can post it to me. I mean, if you can copy and put it onto a Word file, then I will. I can actually write some answers and send it back as an email to you, so that you can share the email.
Yeah, we'll coordinate with the hosts and try to do their recording, no?
Yes. So from the recording, from the chat channel, if you can write down the questions, then I can provide some answers, so that you will all get it as a email, but you'll have to collect the email and all that. So You might have to do something.
Okay. Thank you very much.
Then shall we wind up? Yeah.
Yes.
For that, I think better to copy the chat box now. Once we close the Zoom
better to copy the chat box. Yeah. Better to copy the chat box and put it as an email to me. Then I'll send the email back to Engineer Kamala, and then if you need the answers or anything, just drop her an email so that she can forward that email.
Yeah. Okay.
Okay then.
Rima, you are there?
Yeah, madam. So I'm Trimavidan, a member of Knowledge Sharing Subcommittee of Civil Engineering Sectional Committee. So it is an honor for me to deliver the vote of thanks today now. Actually, first of all, I had to I had to give our thanks to Professor Jayasinghe, who gave the very valuable and very important lecture today, the design philosophy for a medium-rise building of 15 to 20 story range. Now everyone has got actually a lot of knowledge from the lecture, and you sir always encourage us. You always share your knowledge with us. Thank you very much. A big thank for you. And secondly, I must thank the organizing subcommittee and knowledge sharing subcommittee, and also the ISL for hosting this event, and the IT team giving their support. Finally, all of our members who participated today, and thanks for everyone, and stay safe. Good night, all for you. Thank you very much. Thank you, everybody.
Yeah, okay.